When you plug a printer into your computer and it simply works, you're experiencing the result of an engineering decision made in the early 1980s. That decision transformed personal computing from a closed, proprietary system into an open ecosystem where thousands of companies could build compatible hardware. The engineer who made that decision held 3 of the 9 original patents on the IBM personal computer, led the design team at 25 years old, and later developed the first gigahertz processor chip. His name is Mark E. Dean. And if you've never heard of him, that tells you something important about how technological history gets written. Mark Dean was born on March 2, 1957, in Jefferson City, Tennessee. From childhood, he demonstrated both exceptional academic ability and a passion for building things. He graduated high school with straight A's, then earned a bachelor's degree in electrical engineering from the University of Tennessee in 1979, graduating at the top of his class. In 1980, he joined IBM as an engineer, entering the company at exactly the moment when personal computing was about to transform from an enthusiast hobby into a mass-market phenomenon. To understand what Dean accomplished, you need to understand the computing landscape he entered. In 1980, personal computers existed, but they operated as closed systems. If you bought an Apple II, you could only use peripherals that Apple approved or manufactured. If you bought a Commodore, you were locked into Commodore's ecosystem. Each manufacturer controlled every aspect of their hardware, from the processor to the keyboard to the display. This created high prices, limited options, and slow innovation because no third-party manufacturers could enter the market without negotiating directly with the original computer maker. IBM recognized this model wouldn't work for their entry into personal computing. They wanted to create a machine that could be expanded, upgraded, and supported by an entire industry of peripheral manufacturers. But that required solving a fundamental architectural problem. How do you allow external devices like disk drives, printers, monitors, and modems to connect to a computer and communicate with its central processor efficiently and at high speed? The answer was the industry-standard architecture bus, co-invented by Dean and his colleague Dennis Moeller. The ISA bus was a set of electrical pathways inside the computer that allowed data to flow between the central processing unit and peripheral devices. What made it revolutionary wasn't just that it worked, it was that IBM made the specifications open, meaning any manufacturer could design hardware that would connect to an IBM PC without needing IBM's permission or paying licensing fees. Dean and Moeller received US patent number 4,528,626 for this invention in 1985. IBM first brought it to market in 1984 with the PC/at computer. Within years, the ISA bus became the de facto industry standard. Hundreds of companies started manufacturing ISA-compatible expansion cards, memory modules, storage devices, and peripherals. The entire PC clone industry, which would eventually include companies like Compaq, Dell, and Gateway, built their machines around compatibility with this open architecture. Here's the implication most people miss. The ISA bus didn't just make computers more convenient, it created the conditions for explosive ecosystem growth. When any company could manufacture a compatible device without needing approval from the computer maker, competition drove prices down and innovation accelerated. Graphics cards improved rapidly because dozens of companies competed to build better ones. Storage expanded because hard drive manufacturers could sell directly to consumers. Sound cards, network adapters, and countless other peripherals flooded the market, each one expanding what a personal computer could do. This was Dean's first major contribution, but not his only one. He also developed the color graphics adapter, which enabled IBM PCs to display color images. Before this, most computer displays were monochrome, showing only text or simple graphics in a single color. The CGA brought color to personal computing, making graphical interfaces practical and setting the foundation for the visual computing environments we take for granted today. Dean held 3 of the 9 original patents related to the IBM PC. At 25 years old, he was named head of all PC design at IBM, overseeing the teams responsible for developing the machines that would define personal computing for the next decade. But Dean's work didn't stop with the original PC architecture. In 1989, after a decade at IBM, he took a 3-year hiatus to pursue a PhD in electrical engineering at Stanford University. IBM financed his doctoral work, and Dean has spoken about how difficult it was to return to graduate school after 10 years in industry. He arrived at Stanford with deep knowledge of logic design, computer architectures, and bus interfaces, but limited understanding of transistor-level circuit design and silicon processes. Stanford gave him the foundation in custom circuit design that would define the next phase of his career. When Dean returned to IBM in 1992, he joined the company's push into high-performance computing. In 1995, IBM established the Austin Research Laboratory, focused on advanced circuit design and developing techniques for high-performance microprocessors. Dean became director of the lab in 1997. That same year, he was inducted into the National Inventors Hall of Fame alongside Dennis Moeller for their work on the ISA bus. He was also named Black Engineer of the Year. In 1998, Dean's team at the Austin lab achieved something the semiconductor industry had considered nearly impossible. They developed the first CMOS processor capable of operating at 1 billion cycles per second, 1 gigahertz. Before this breakthrough, the fastest processors operated at less than 300 megahertz. Dean's team didn't just incrementally improve performance, they shattered the ceiling of what engineers thought was achievable. The gigahertz processor had immediate implications for internet infrastructure. As the New York Times reported in 2000, the demands of the internet and e-commerce created a voracious market for processing speed, and web servers would be the first major application. Dean's chip arrived exactly when the internet economy needed it, enabling the server infrastructure that would support the explosive growth of online services in the early 2000s. After leading the Austin lab, Dean assembled a small team in 1999 to work on an even more ambitious project, the Blue Gene supercomputer, designed to be both powerful and energy efficient. In 2004, Blue Gene clocked in as the fastest supercomputer in history. It ushered in an era of high-performance computing that valued efficiency as much as raw processing power, a design philosophy that remains central to modern data center architecture. Dean's career at IBM spanned more than 3 decades and included leadership roles across research, development, and strategy. In 1995, he became the first African American ever named an IBM Fellow, the company's highest technical honor. He served as Vice President of Performance for the RS/6000 division, directed the Austin Research Laboratory, led the Almadon Research Center in California, with its 400 researchers focused on database and storage technology, became Vice President of Worldwide Strategy and Operations for IBM Research, and later served as Chief Technology Officer of IBM's Middle East and Africa business. In 2013, Dean left IBM to return to the University of Tennessee, where he became the John Fisher Distinguished Professor in the College of Engineering. Throughout his career, Dean accumulated more than 20 patents. His innovations span the entire arc of personal computing, from the architectural decisions that made the PC ecosystem possible to the high-performance processors that power modern internet infrastructure. Yet, despite holding 3 of the 9 foundational patents on the IBM PC, despite leading the team that designed it, despite developing the first gigahertz chip and contributing to the fastest supercomputer in history, Mark Dean's name remains largely unknown outside engineering circles. This invisibility follows a pattern that extends across the history of technology. When innovations succeed and become infrastructure, the individuals who created them often disappear from public memory. The systems simply work, and users don't think about who made them work. But Dean's case also reflects a more specific pattern of erasure. Black engineers and scientists have consistently contributed to foundational technologies while receiving minimal recognition in popular narratives of innovation. We see this with Gladys West, whose mathematical modeling of Earth's shape made GPS possible but remained unknown until 2018. We see it with Katherine Johnson, Dorothy Vaughan, and Mary Jackson, whose calculations enabled space exploration but were nearly forgotten until Hidden Figures brought their stories to light decades later. The pattern is clear. Black scientists build the infrastructure that shapes modern life, but the credit goes to institutions, companies, or individuals whose contributions came later in the development chain. Dean's work on the ISA bus created the open architecture that allowed the PC industry to flourish. Without that decision to make the specifications open, personal computing might have remained locked in proprietary ecosystems where a handful of manufacturers controlled everything. The competitive hardware market that drove prices down and innovation forward only existed because Dean and Moeller built a system that allowed it. Similarly, Dean's gigahertz processor didn't just break a technical barrier. It arrived at the exact moment when internet infrastructure needed dramatically more processing power. The web servers, data centers, and network systems that enabled the internet economy relied on the kind of performance Dean's chip delivered. These aren't isolated achievements. They're structural contributions that enabled entire industries. Yet the popular history of personal computing rarely mentions Mark Dean. Narratives focus on entrepreneurs like Steve Jobs and Bill Gates, or on companies like Apple, Microsoft, and Intel. These contributions are real and important, but they built on foundations that engineers like Dean created. The ISA bus made the PC clone industry possible. The gigahertz chip made high-performance internet infrastructure possible. These enabling technologies don't get the same attention as finished consumer products, but without them, the consumer products couldn't exist. Dean himself has spoken about his career in ways that emphasize problem-solving over recognition. He's described his leadership style as helping others get things done, focusing on clearing obstacles so teams can achieve their goals. He's encouraged young people to pursue graduate education, but acknowledged the challenges of returning to school after time in industry. He's advocated for diversity in engineering, speaking at high schools and colleges about the technological accomplishments of African American engineers. In interviews, Dean has demonstrated a forward-looking perspective that prioritizes what technology can become over what it has been. In 1999, he described his vision for a magazine-sized, voice-activated tablet computer that would be inexpensive and programmable. This was years before the iPad, years before tablets became a mainstream product category. Dean saw where computing was heading and worked to build the technologies that would make that future possible. The story of Mark Dean's contributions to personal computing challenges several assumptions about how innovation works. It demonstrates that foundational technologies often matter more than finished products, even when finished products receive more attention. It shows that open standards and architectural decisions can shake industries as profoundly as any individual device. It reveals that the engineers who solve enabling problems rarely receive the recognition that entrepreneurs and marketers do, despite creating the infrastructure on which everything else depends. When you connect a device to your computer and it simply works, you're experiencing the result of decisions Mark Dean made in the early 1980s. When you browse a website that loads instantly, you're benefiting from processing power that Dean's team made possible in the late 1990s. When you use any system built on open hardware standards, you're operating within an ecosystem that Dean helped create. His work is embedded in the infrastructure of modern computing so thoroughly that it's invisible, and perhaps that invisibility is the truest measure of how foundational his contributions actually were. The systems he built don't announce themselves, they just work reliably, universally, exactly as intended.